Redox reactions. A redox reaction stands for something known as a reduction and oxidation reaction. And here what you can see is a single displacement reaction in which magnesium is displaced in iron to form magnesium oxide and elemental iron. But the story is a little bit more intricate than what we have discussed thus far. Specifically, if you look at the charges of the elements, the story becomes a little bit more complex. For instance, take a look at iron. Within iron oxide, iron has a 3 plus charge, but by the time the reaction is over, the charge of iron has gone down to 0. And in a similar manner, magnesium that started with no charge has now developed a 2 plus charge. Now that we kind of already knew because the process of single displacement reactions does entail the fact that charges have to change. But because the charges are changing, what that means is that the amount of electrons present in the species is actually changing when you go from reactant to product. Specifically, if we look at iron, we have a charge of 3 plus to begin with, and we end up with a charge of 0. If you literally subtract the charge of the reactant with the charge of the corresponding product, you have 3 minus 0, which is plus 3. And we write that as plus 3 electrons, meaning that you are acquiring 3 electrons for every iron center that you have. Anytime that you acquire electrons, we call this a reduction. Similarly, looking at magnesium, you start with a charge of 0 and you end up with a charge of 2 plus. Subtracting those charges in that order, 0 minus 2, gives us minus 2 electrons as the overall exchange of electrons going on for magnesium. Minus 2 electrons for magnesium, we call this the oxidation. Anytime you lose electrons, you are oxidizing the species. One thing that I will also remind you of is that the reactant species that is undergoing reduction is also known as the oxidizing agent. The reactant species that is undergoing oxidation is also known as the reducing agent. And the idea is that whatever is getting oxidized has to come at the expense of something getting reduced. That's the reason you have this almost nonsensical way of naming the species. But when you think about it, it does have a reason to it. Specifically, that the electrons cannot be free floating in solution. Whatever electrons you produce from one species, they have to go to the other species. And that in and of itself is the premise of balancing a redox reaction. Now notice that the way I've written the reduction and oxidation in terms of electrons is based on a ratio. 3 electrons per iron and minus 2 electrons per magnesium. Now that doesn't take into account the fact that we have different proportions of these elements. Specifically, we have 2 irons total in the reaction and we have 3 magnesiums total in the reaction. So what you want to do is multiply the ratios by the amount of the element present, 2 irons or 3 magnesiums. What this will do is cancel out the irons in your fractions, the magnesiums in your fractions, and you end up with 2 times 3, which is 6 electrons, and 3 times minus 2, which will be minus 6 electrons. And right here, very clearly, it shows that any electrons lost in the oxidation process are gained in the reduction process. You will always have one with the other. Alright, so that basically tells us the story of a redox reaction. Now for single displacement reactions, this entire analysis doesn't need to take place, but as you'll see in the next video, the balancing of redox reactions in water in solution is a little bit more intricate, and we're going to discuss that next.